with Ampere's circuital law. What was Ampere's circuital law? Line integral of magnetic field, that is B dot dl. This is equal to mu naught times the current which is enclosed. We had seen two applications also of this. One was solenoid, other was a toroid. So what was the formula of a solenoid? B is equal to mu naught Ni. Now N is not just number of turns. We have to consider N as number of turns per unit length. So if you just have N given number of turns and divided by the length to get the number of turns per unit length. So this is the formula that will be used, but just be careful when you're using N. N's value, N's definition over here is number of turns per unit length. So not just include only the number of turns. One question, let us see. We didn't practice any questions, no? See a solenoid coil of 300 turns per meter is carrying a current of 5 amperes. All right, length of the solenoid is given as 0.5 meters and the radius is given as 1 centimeters. You have to find out the magnetic field inside the solenoid. Now, in this case, length is given as 0.5 meters. Radius of the solenoid is given as 1 centimeter. So how will you decide which formula you have to use? See, two formulas we have studied. If it's a long solenoid, we use B is equal to mu naught Ni. And for short ends, we use mu naught Ni by 2 if we are talking about the ends. So here, how would you determine whether it's a long solenoid or not? It's not given that the ends of the solenoid are extending up to infinity. So how will you decide now? So see, length is given as 0.5 meters and radius is given as 1 centimeter. So if you see the condition, no, when the length is very much greater than the radius, see, it's like small number of turns are made and a long solenoid is made. So if length of the solenoid is very much greater than the radius of the solenoid, then you can conclude the fact that this is a long solenoid. Then this is a long solenoid. So length is 0.5 meters and radius is very small, that is 1 centimeter. All right, so length is very much greater than radius, so it's a long solenoid. So once we know that this is a long solenoid, we can apply our formula B is equal to mu naught Ni. Now, what is mu naught? Mu naught is the permeability constant whose value is 4 pi into, yes, very good, Tari. 4 pi into 10 to the power minus 7. This is the value of mu. Now, N is number of turns per unit length. What it is given? 300 turns per meter. That is number of turns per unit length. So this is given exactly like this. Small n is given to us. So we'll multiply it by 300. And the current is given as 5 amperes in the question. This is current is 5 amperes. So this becomes into 5. So magnetic field will become, this becomes 60 pi into 10 to the power minus 7 into 10 to the power 2. So finally, I'm leaving it in terms of pi, 6 pi into 10 to the power minus 4 Tesla. This is the magnetic field. Note it down. One more question we'll do that I'll do with the help of discussion. So if you have not understood anything in this question, let me know. The next question I'll discuss. Okay, next question says a solenoid of length 0.5 meters has radius 1 centimeter. It is made up of 500 turns. Current is given as 5 ampere. We have to find out the magnetic field's magnitude inside the solenoid. So now this I have discussed. This is a similar type of question. Length is 0.5 meters. Radius is 1 centimeters. Yes, Austin. Is it a long solenoid?
No, ma'am. I mean, yes, it is. It is
Reason?
long solenoid.
Yes, Austin.
It is a long solenoid.
It's a long solenoid. Reason is that?
The length is greater than the
Length
radius.
is greater than the radius. This is the reason. See, it's a long solenoid. Length is very much greater than the radius. So we can say it's a long solenoid. Once we know that it's a long solenoid, we can directly use this formula B is equal to mu naught N I. This formula is now applicable. Yes, Alia, what is mu naught's value? What is mu naught? How much, Alia? Yes. Alia, you're not audible. Pfizer. 4 pi into 10 to the power minus 7. Very good, Faisal. 4 pi into 10 to the power minus 7. That is the value of permeability. Because the constant that we get from Biot-Savart-Sloyd's formula is mu naught divided by 4 pi. And the value of mu naught divided by 4 pi is 10 to the power minus 7. So only if you want to find out the value of mu naught, that becomes 4 pi multiplied to 10 to the power minus 7. Very good. Yes, this is 4 pi into 10 to the power minus 7. Value of small n that I should put from the formula. Yes, Humam. Small n. Humamuddin, what is the value of small n that I should put? Madiha?
500.
500. 500 you're saying?
Yes, ma'am.
What is the meaning of small n in the formula? Did you attend the last class? What is the meaning of small n? Just the number of turns. Is it just the number of turns?
Per meter.
Number of turns per unit length. This is what is the difference from this question. Here we were given number of turns per unit length. 300 turns per meter was given. Right now in this question only 500 turns, that is number of turns are given. So it means small n we have to find out number of turns per unit length. Number of turns are given 500, length is 0.5. So that becomes 1000 turns per meter. So you have to put 10 to the power 3. Let me write it as 1000. And current is given in the question as 5 amperes. This becomes it. So this is 2 pi 20. So 2, 3 minus. This is 2 pi from here, 20 pi. Let's take the 0, that becomes 10 to the power 4. So minus 3 into 10 to the power minus 3 Tesla. This is the answer. So be careful, class, whether it's number of turns given or number of turns per unit length. Otherwise, your entire question will go wrong. See, this is the difference between the question 1 and question number 2. Quickly note it down. Then we'll start with toroid. Solenoid is completed till here. We'll start with toroid. Coming to toroid now. Now see if you've understood solenoid, no, toroid is not very different from solenoid. It's just that slight differences are present. That too in number of turns per unit length. See, if you take a wire and you turn it in the form of coil, just make it a helical form of it, that we call it as a solenoid. This is what we had studied in the last class. If I join the circular ends, this was a solenoid. If I join its circular ends, so if we join its circular end, now the device that we'll obtain is known as a toroid. See, like this. Solenoid was a straight wire. So if a solenoid is bent in the form of closed ring, that is what we call as a toroid. And it's written also, I think. Yeah. A solenoid bent into the form of a closed ring is called a toroid. So if you are just bending it in the form of circle with leaving one edge as open, that gives you a toroid. So just the difference is that number of turns per unit length becomes different. Why? Because when you have a straight solenoid, length is L, but as soon as you have a circle, now for a circle, length of a circle is the periphery of it. So it's different. So a solenoid bent into the form of a closed ring is called a toroid. See, if you when we did the derivation, because derivations of solenoid also come separately in the exam and derivations of toroid also come separately in the exam. See, when you have the derivation for a solenoid, that time what happened? Solenoid was there. If we cut it into half, we took the transverse section and we did it, the derivation. Here also we are going to do the same thing. If this is in the form of circle, we are going to transversely cut it. Like this it would appear. Outer part will appear like a concentric circle. So it's like from here the current is coming outwards, going inwards, then coming outwards, going inwards, coming outwards, going inwards, in the form of spiral like this. Current is coming outwards, then going inwards, coming outwards, going inwards. So this is exactly how we have to put it. Transverse, see. Horizontal, when I say, if suppose this is my solenoid, when I say I'm cutting it horizontally, horizontal or transverse is same, Faisal. All right, when I say if we have certain times we have to do the calculation, we cut it like this, right? Now my device is like this. So I am cutting, instead of cutting it like this, I am cutting it like this. See, horizontally if you cut it. So transverse is horizontally only. Your question is right. Transverse is actually horizontal if you cut it like this. All right. So it's how it helps us is that we are able to see it from above, how the current is coming and how the current is going. You can do the derivation in the form of this only. Toroid also, but see, it would be so confusing for you. From which point will you mark outwards? Here in this only you'll mark outward, inward, and all the regions. So that becomes confusing. That's why. And in NCERT also, standard way to solve this is using this. Now I'll divide it into 3 regions. Let's say this is region 1. That is inside. So this is my Amperian loop. Remember Amperian loop we studied. Let's say the radius of Amperian loop is R1, right? So R1 is what? It is the space interior to the toroid. So when I'll integrate it, B dot dl means I'll apply Ampere circuital law. B dot dl is equal to mu naught I enclosed. This is my Ampere circuital law. See, B into 2 pi R1 is equal to mu naught I enclosed. But problem is that magnetic field isn't present in the center. If magnetic field isn't present in the center, this is 0. Right? We don't have any magnetic field present at the center. And what is I? I is current in a single loop. Means basically current of the circuit, current in a single loop. So in the region 1, we are getting it as 0. Now, let's talk about region 2. So what will I do now for region 2? This is region 2. The part which is covering it, this is region 2. A portion of magnetic field is also included and it's not completely outside also. So some portion is included, some portion is excluded, right? This part I'm saying. See, if these are the concentric rings, no, I have taken my Ampere circuital, my Amperian loop like this. Earlier it was like this for inside. This is now for outside. Now see, let's say radius is R2. Radius is R2. We'll apply N is the number of turns in a toroid, number of turns. Now for region 2, we'll apply Ampere circuital law. So integral, closed integral of B dot dl, that is line integral of magnetic field, is mu naught times the current that is flowing. N number of turns are flowing, so we should write it as IN. Now magnetic field, what is the dl for that? Means entire length. Entire length is 2 pi R2 is equal to mu naught N I. So what is the magnetic fields formula? Mu naught Ni divided by 2 pi R2. Fine, this is also done. Now let me choose a region 3. This is region 3. The outermost I have chosen as region 3 because we have to cover every space, no? So this region is 3. Again, no need to perform any calculation. Directly in region 3 also it is going to be 0. Why it's going to be 0 in region 3? Because you already know there is no presence of any magnetic field over there. Magnetic field is present in region 2 only. In region 3 also this is 0. So if I add all the magnetic fields, I just get, see, from the first region it's 0, from second region it's something, from third is also 0. So what has to be the net magnetic field? Mu naught Ni, and since now only one magnetic field is there, so no need to differentiate between R1 and R2 and R3. Directly write it as R only. R is the radius of the loop. Now, what is, if you look here, are we getting something? If you notice here, this is N divided by 2 pi R. Number of turns per unit length, per the unit, the circumference of it. See, just focus on this. N by 2 pi R is there, small r. What is N? N is the number of turns. And what is 2 pi R? 2 pi R is actually the length of a toroid, of the toroid, right? So this is length of the toroid. Number of turns and length. Earlier, when it was a straight solenoid, we just had the length as L. Now it is in the form of circle. So this is what we are writing. So how do we write number of turns per unit length? We write it as N, number of turns per unit length. We write this as number of turns per unit length, right? So what do we have as the formula? Final formula of this becomes B is equal to C. The final formula becomes B is equal to mu naught Ni again. Difference is that the formula of N, small n, is N by 2 pi R, not N by L just. This is your toroid and the derivation is also simple. Note it down. Any doubts you are having, get it clear in between. I was checking your papers. I had checked your papers of the DC circuits which you gave. So Austin, you had attempted it very well. I think the best papers was yours only. So I hope you have performed all the questions on time only, Austin. No extra time you had taken. All right. Regarding the rest of you, the simple questions, you all have attempted it well. Do not go by the score for this particular test because this was just full of the circuits. So the score is not very good by all of you, but the attempt that you have done is fine. You all were able to at least attempt it. There was one question where 6 parts were there. That you all have attempted it well. The individual questions, somewhere you got stuck, and 1 or 2 students were not able to do the first question as well. That was not 0.1 amperes was the answer. A triangular circuit was made. So if you are scoring 10, something like this, 11, 12, because many students, 3 students I remember have scored 12.5 only. So you just practice it once, because I know it was just full of circuits, so it can happen. Otherwise, you people have attempted it. But those who are getting 10, 11, 12.5, please just practice it once and send me it as an assignment. So it would be helpful for you only. And Rabba, tomorrow, I'll inform you. See, tomorrow, most probably, are you available on Saturdays and Sundays at 9 p.m.? Tomorrow, at least for tomorrow, 9 p.m. Are you available, Rabba?
Ma'am, in morning,
No, 9 p.m. IST timing here.
like India state timing 9 p.m. So it will be here 7 around.
It would be what would be the timing for 9 p.m. 6:30, I think. 6:30 KSA timing.
Ma'am, can we do it in the morning? Is it available? Like, are you available?
Morning, actually, in one batch it is going to be repeated. So if you could join that for just few classes, or okay, next week can you join, because in the first classes they are just the initial classes of it. What about next week? Means can you make yourself available for Saturday and Sunday just for the next two?
Okay, ma'am. In the
Okay,
evening,
next
I will
Saturday,
try.
Sunday at least you can. Then rest of the classes, I'll take your separately. All right. Wherever
No, ma'am,
I
it's not it separately. Okay, but if it's possible, it can be in the morning with the other batch. It's okay.
okay in the morning on Sundays.
Sundays, Mondays is my summer vacation, so I can take any time in the morning.
Acha, your summer vacations are going. Okay, then we can arrange a class on Sunday morning as well. Your summer vacations are going. Fine.
Okay. Thank you, ma'am.
B is 0 because see, if you look in the figure, there is no magnetic field that is enclosed within this first region. All the magnetic field is present within the solenoid, within the toroid only, right here only. So here in this region inside or outside, there is no magnetic field that is present. That's why we have taken it as 0. See, in the last class, we had done a question where through Ampere circuital law, we had calculated for a wire, the magnetic field inside a wire and outside a wire. Do you remember this question? This one. See, I told you this is important also because some questions, in some questions, the values will be given and you have to find out the answer. So for that case, you have to remember the formula also. All right. So these two questions, this question we did where I had told you both the parts, where a magnetic field inside a wire of radius A and outside a wire of radius A, where Ampere circuital loop's radius was R. So see, this was the formula inside we were getting. B is equal to mu naught I into small r divided by 2 pi A square. And for outside, we had the formula B is equal to mu naught I divided by 2 pi small r. Now see, you have a graph also in your syllabus. That graph repeatedly, it came also repeatedly and it can come also in your school's exams also and in your main board exams also, where you have to tell the relationship or you have to plot the graph between magnetic field and the radius of Ampere circuital loop. All right, this radius and the magnetic field you have to tell. So for that, you have to remember these two formula also because they can separately also come. The derivation also can come and separately they can come. So see, outside inside the formula came mu naught IR divided by 2 pi A square, and outside it came mu naught I by 2 pi R. So if you plot a graph in single graph and you have to show both the cases, so see, R is equal to 0 is at the center, R is equal to capital R, that is the Ampere circuital loop's radius and the radius of wire. Both are equal. So see, if from the center to the surface, we are calculating the radius, it means it is somewhere between from the center and to the surface. So anything in between, this is inside. So what did we see? What is the relation inside? See, magnetic field, this is directly proportional to the radius. This magnetic field and radius, they are directly proportional. So till the surface, they are directly proportional. B is directly proportional to R. So this is the case inside. Now what about outside? You can look the formula. B is inversely proportional to R. So if it is inversely proportional to R, this will be a hyperbologram. So B is inversely proportional to R. This is outside. So this graph can also come. This is in relation with the previous question. All right, that completes with Ampere circuital law, but make this as a note point and plot this graph as well. And that's why, and try to remember these two formula also, this formula and this formula for inside and outside. Done till here? Completed? All of you have completed till here?
Yes, ma'am.
Only Rabi has completed.
Yes, done.
All right, so all of you have completed. Fine. See, Ampere circuital law is over. This was Ampere circuital law. Now, whatever will be the usage, it will be from this one. Now we have certain forces. All right. In Ampere circuital law, till Ampere circuital law, actually, when you use Biot-Savart's law, when you use this Ampere circuital law, in both the laws, you're trying to find out the magnetic field only, right? Here also, we were finding the magnetic field. There also, from Biot-Savart's law, also, we were trying to find out the magnetic field, right? Now we'll find out the forces. This is a little lengthy part, magnetic Lorentz force. This won't be completed in one class today. Tomorrow also we have to study this. Most probably by tomorrow or in the next class it should be completed. This is the lengthy topic which is left. After this torque part is also very small. And this conversion part is also very small. Force is also not very lengthy. This part is actually lengthy. See, if a charge is moving with velocity v in magnetic field B, so you don't have to derive it because this is through cross product. So directly remember the formula. So magnetic force FB is Q V cross B. This is the formula. So cross product. Yes, Rabba, do we use sine theta or cos theta with cross product? Sine theta or cos theta? V cross B is there. So VB sine theta or VB cross theta? Cos theta. Humam, you've studied this. Recently also we had a class about this, Humam. Sine or cos? Yes, Humamuddin. Right, Tariq. See, sine theta we use. Formula of magnetic field becomes Q, magnitude of V and sine theta. When you have dot product, that time you multiply the magnitudes with cos theta. When you have cross product, then you take sine theta. Fine, so this is it. Now, if they are parallel, suppose example, this is magnetic field, charge Q. This is moving in the direction of magnetic field only. So here you will directly apply F is equal to FB is equal to QVB sine 0 degree. That will become 0. Whatever you can use, whatever you want. Now, one question that comes, which I want to discuss with all of you. See, one question, this is a little difficult if you look at it without understanding your class 11's perspective. The question is, if force is perpendicular to velocity, then what is the change in kinetic energy? This is the question. All right. If force is perpendicular to velocity, this is the actual question. If force is perpendicular to velocity, then what is the change in kinetic energy? So see, if force is perpendicular to velocity, it means it is also perpendicular to displacement. What is the formula of velocity? In your class 11th, you must have done, no? Velocity is ds over dt. That is change of rate of displacement. So if this something is perpendicular to velocity, it will also become perpendicular to displacement, right? So, and if force and displacement are perpendicular, means the angle between them would be, this implies that the angle between them would be 90 degree. So in our formula of work done, the formula of work done is F dot S. Now dot product. For dot product, we use cos theta. So this becomes Fs cos 90 degree, which is 0. Work done is 0. Clear? First, tell me, till here it is clear, no? Work done by the magnetic force is 0.
Yes, ma'am.
Faiza, Madiha, Rabia, clear? Till here?
Yes, ma'am.
All right. See, once we know that magnetic forces work done is 0. Can any one of you tell me in class 11th we had done one concept which is known as work energy theorem? Can anyone tell me what was work energy theorem? Yes, Madiha, can you try? Or write down, just type it in the chat column. Work energy theorem, work kinetic energy theorem.
Ma'am, it was the total work done by the forces acting on a particle is equal to the change in the particle or in the energy.
It is equal to
The change
in
the energy of that particle.
kinetic energy. Very good. See,
Kind of.
work energy theorem, she's right, Rabba is correct. Basically, whatever is work is done not just by a particular force, Rabba. It's by any object, it's by any action. Half mv square is the formula of kinetic energy, not just half mv tari. Half mv square, that is the formula of kinetic energy. So work done, whatever work is done, this is equal to change in kinetic energy. So if from the force which is perpendicular to velocity, we have to link how to get kinetic energy. So we have calculated that work done is 0. So we'll apply work energy theorem. And what is work energy theorem? Work energy theorem basically says that whatever is the work done, this is equal to change in kinetic energy. So if work done is 0, then change in kinetic energy is also 0. This means final kinetic energy minus initial kinetic energy is 0. That is, there is no change in kinetic energy. That was the question. There is no change in kinetic energy. Also, one question which can be extension of it is that what happens to velocities then? So see, half mv final square is equal to half mv initial square. Now half m would get cancelled. So final velocity is equal to initial velocity. So there is no change in velocities as well. Why is this happening? This is happening due to the magnetic force. This is happening due to the magnetic force. So if a little difficult, tricky question comes in your exam, from force, it can relate your velocity or kinetic energy or work done. So you just have to keep this in mind. Condition will be given to you that if force is perpendicular to velocity, if force is parallel to velocity, you know now theta will change, so work done will exist somewhere. But usually the question is force is perpendicular to velocity. This rarely comes in exam. This is not a very common question, but it has come. And it's a difficult question. So if directly it comes, it sometimes becomes difficult to relate it to work energy theorem. So note it down so that you have an idea. Then we'll see there are 4 cases in your syllabus which we have to study. That we'll see, but first note it down from here. Magnetic Lorentz force from here. So yes, magnetic Lorentz. So this is actually the formula. Electric force was something which we had studied in the first lesson. This is now magnetic force. So till now we didn't discuss anything regarding the force. So this is the first time in magnetics we are discussing the force. See, now individual cases, there are 4 cases which you have to remember. First 2 cases are very easy. Cases as in velocity, magnetic field, what are the direction, how is the charge placed. So first case is very easy. See, if charge particle is parallel to magnetic field, so theta will become 0 degree. So in the formula of magnetic field, QV B sine 0 degree, magnetic force will become 0. This is one case. Rest, any angle can be given to you. Any way you can solve it, but these are 4 cases which separately come in your exam and which are mentioned in your NCERT specifically. So instead of going, because now once you have all these notes, you do not have to go through NCERT. I already mentioned you in the class. If something is extra, that also I mentioned. So just rely on these notes completely, but revise it once before coming to the next class. See, if they are anti-parallel, theta is 180 degree. So force will become QVB sine 180 degree. Again, the same thing. FB will become 0. 2 cases clear? Third case is a little different case, not simple as theta 0, 0, 90 degree something. See, if the charge particle, this is the third case, if the charge particle is along this direction. So we have to find out the direction of force. So how to find out the direction of force? See, in which direction is the direction of motion? Means the direction of velocity. Put your hand in that direction. Right hand. Again, we will talk about right hand thumb rule only. Suppose this. Look at this point. So velocity is downwards. So I'll keep my right hand downwards. All right. And where is the magnetic field going? I'll keep my hand like this, right? Downwards. When you will do in the sheet, it will become clear. It's difficult to show it on the screen, but you can do it alongside with me. So see, this will be downwards. Now, where is the magnetic field going? The cross sign symbolizes that magnetic field is going inwards. So curl your fingers inwards. Thumb gives you direction of force. So this is the direction of force. Come to this. See, it's a little easier to show in this part. Velocity, put your hand in the direction of velocity. Your fingers in the direction of velocity. So fingers are moving towards, the velocity is moving towards the right. So your fingers will also move towards the right. You can keep it like this also. You can keep it like this also. But magnetic field is inside. I have to curl the fingers. So if I keep the fingers like this, I'm able to curl it inwards. If I am keeping it like this, I'm not able to curl it inwards, right? So if this is the magnetic field, curling magnetic field inwards, force's direction is upwards. This is the direction of force. Now, all of you quickly in the chat column, tell me the direction of force here. Up, down, right, left, how? What is the direction? All of you. Very good, Austin. Austin has already answered it. Keep your hands along the direction of velocity. Curl your fingers towards magnetic field. Thumb will give you direction of force. Except for Austin. Others. Madiha, your answer. Rabia. Humam. Rabah, Faiza. Faiza, 2 directions you are saying. Down
Ma'am,
also.
you're asking for which one? Can you add again? The up one or the right hand one?
See. When the velocity is going up, so you keep your hand up, curl your fingers towards the magnetic field. Magnetic field is inside, inwards, right? So curl is inwards, leftwards it's going. So it's directly leftwards. For both of them, acha, for this also you were answering, Faiza. Yes, answer to this. Madiha, you have answered just now for this one. Okay. Others, Faiza, for this part. This is leftwards, all right. For this. Good. Downward. So okay, Faiza, you were answering for both the parts. Now I get it. See, velocity is towards the left. Fingers are curling inwards. So this is going downwards. So basically, why did we study this? Actually, if you join all the movement of the particles, these are just 4 points I have taken. If I completely join all the 4 points, this will move in the form of circle with force acting towards the center. See, force is acting towards the center. Direction of force is pointing towards the center for all the parts. So this is a unique case for you. This is not similar to the question which we did. When the charge is moving in the form of circle, force is pointing towards the center. This is your third case. Now, this is related to your uniform circular motion in class 11th you must have done. Can you name the force which acts towards the center? Along the radius towards the center, a force acts in the circular motion. Centripetal force. Very good, Faiza and Austin. Centripetal force. So we'll relate now this magnetic field with centripetal force and get the rest of the derivation. So this is a different case for you. It's not like you just have to put, no, we have been doing questions, unstable equilibrium, stable equilibrium, theta 0, 180, 90. All right. And this is the directions are also given, which I was telling you. Place your fingers along the motion, curl your fingers towards magnetic field, thumbs give direction of magnetic force. So you now have the direction of magnetic force as well. Just make the heading as special cases. There are 4 cases. 2 are very easy. Third one, little derivations we have to do. Fourth one is completely theoretical. That also we do. But firstly, note down till here. if you have completed till here, you people can start leaving. Tomorrow we'll complete with this topic. Thank you so much, class.